Hi, welcome back. In this session, we will look at variables, a very important abstraction provided by programming languages. So in brief, this is our agenda. We will look at why programming languages provide variables, and we will also look at the most important properties that are attributed to variables that kind of define their meaning, beginning with the most important of those attributes, which is names, and then followed by a definition or an overview of what these different attributes are, how they can be bound, and what different binding times are. Then we will look at some of the other most important attributes that can be bound to variables, like scope, access rights, and storage and lifetime. Right? Okay. To understand why we need variables, let us look at a simplified version of the von Neumann architecture, which is the basis for many programming languages, especially the imperative ones. Of course, I'm going to be using a very simplified version. Modern architectures are much more complex. But the important takeaway from this is that there are two main components of every von Neumann-based machine, which is the memory, which stores the content or the data, and then the processor, which does things using this data. Memory are generally organized into memory cells, for which variables provide a very apt abstraction. So this is why or what variables are from the architecture. So now, to understand variables, we need to understand names, which, as we will see, is one of the most important properties we can attribute to a variable, among other things, right? So names are one of those things that differentiate high-level languages from languages that are used, for example, for pocket calculators, where you can only perform computations without ability to reuse memory locations. Of course, modern calculators may also provide such functionalities, but let's keep that aside. So in general, names allow sharing of data across your programs. Let's look at this small example where the name x is assigned to the value or bound to the value 10, and the value of x is now reused to compute the value of y. So by allowing information sharing, they also enable a reuse of data and memory locations. In general, most names allowed in programming languages are combinations of digits, numbers, and symbols, but we'll still need to have some considerations like what is the impact of the allowed length of the names is in a particular language, what is the impact of special words are. We will look at these in the next slides. So the first consideration to see is what are the impact of the allowed form of name is in a particular language. Generally, as I mentioned before, names are combinations of letters, digits, and underscore. What is a valid name varies by language. Most modern languages encourage the camel case notation, where you have first prefix of the name, which is in small letters, followed by a caps, which begins every subsequent word. Right? Languages like PHP prefix all of the allowed variables with the symbol $. And languages like Perl have different prefixes that define what is the type of the language itself. So the name itself carries one more binding, which is type, right? As mentioned before in my previous lecture, and also now, types is a separate beast to cover, which we will dedicate 2 other sessions to at the end of this lecture. So languages like Ruby use @ to indicate that your variable is an instance of a class, right? In general, length also has an impact on what you can do with the name and what the implications are to your program's readability itself. For example, if the name of your variable is too short, right, that means that you cannot use the name to communicate multiple messages at the same time, meaning they are not connotative. And variables generally are better off being a little bit more descriptive, as it enhances readability of your whole program, right? But at the same time, having it too long can also have complications. In general, some of the common length conventions or rules in languages are, some examples are that C99 has no limit, but only the first 630 are significant, and external names are limited to size of 31. Now, this is kind of, although I mentioned that having the name descriptive can have advantages, having it too long, as you can imagine, can also hamper readability. So some languages go out of their way to enforce that you should not have more than so many characters. C# and Java have no limit, and all of the characters are significant. C++ also has no limit, but many implementers impose one. But in general, the idea is to make sure that you provide a name that is as succinct as possible, but also is able to communicate everything that the variable does, right? Or everything that the variable is kind of responsible for. Case sensitivity is also a restriction that some languages put on the names. For example, a variable with ABC all in small is different from a variable with ABC all in big. Now, although case sensitivity improves readability, it can hamper maintainability of the names, because it's very much possible that one developer of a program just uses a variable and names it A1, and another one creates another variable called big A1, and both of them would not be in conflict with each other and continue to exist in your program and compile, run, and everything. And then after a few years, a new developer may come and he might want to reuse one of them, and then if he's not aware that your language is case sensitive, use a different version of the variable that he meant to, and still end up having a program without compilation errors. And this, as you can imagine, would cause chaos later. Right? So in general, the point is that the form of the name, both the allowed form of the name from the language and also the recommended form of the name, have an impact on the readability and the maintainability of your program. So, and as I mentioned, another factor to consider when using names is special keywords. Some special words are words that have special meaning. For example, here, if, while, return, all of them have different meanings, and they are dedicated meanings from your programming languages, provided by your programming languages to these names. So there are two kinds of special keywords. One are the reserved keywords, like modern languages such as Java and C have reserved keywords. For example, if is a reserved keyword, right? Meaning they have a specific purpose, and this purpose is fixed throughout your program. So you cannot reuse it for any other purpose. But some languages, for example, like Fortran, have the concept of keywords, right? Special words are considered as keywords, meaning they have a fixed purpose only in a particular context. So you can reuse them as normal variables to mean different things in different parts of the programs. Here is a program that I composed on Fortran, which is completely valid, right? So it adds two numbers. It declares three real numbers. One of them is called integer, which is again a keyword in another context. One of them is called real, and another one is called if. And I'm assigning the value of if to 12 and the value of integer to 15. And this is completely valid to write a program that says if equal to 12, then real equal to if plus integer and if. And then you print the value, right? So generally, modern programming languages take the approach that they try to avoid keywords that can have different meanings. So they reserve special words for specific purposes, and they cannot be reused for any other purpose. In the next session of our lecture, we will look at bindings. We have actually seen one binding that can be associated to variables, aka names. We will see a bunch more properties that can be attributed to variables using bindings. On a high level, bindings provide meanings to variables. And generally, these bindings are introduced when a variable is defined or redefined in different parts of your program in languages that allow you to do so. Let's look at an example from C. This const double val equal to 23. This particular statement definition binds 4 different attributes to the variable. One, the const says that this particular variable cannot be modified in a later part of the program. It restricts the read access to this variable, write access to this variable. It binds the type double to this variable. Then it binds the name value to this variable, val, and it also binds 23 as a value to this variable. So in brief, these are the different attributes or bindings that are commonly associated with variables. We've already seen the first one, which is name. which says that this particular variable is identified this particular identifier or name. The next one is scope, which says that your variable is visible only in certain subsections of the program. The next one is type. As mentioned before, we will have 2 separate sessions at the end of this course to discuss types, but on a high level, types restrict what kind of values can be stored in this particular variable, right? For example, integer, if a variable is bound with the type integer, then only values which are numbers and are integers without decimal points can be stored in this particular variable, right? The next one is value, which also we already saw in the previous slide, which essentially says what value can be stored inside this variable at this particular, or it says what is stored in this variable at this particular moment currently, right? And the next one is lifetime, which essentially says when the variable was allocated and when it is deallocated, meaning it exists in this universe of your program only at between these points. Lifetime and scope sound like the same thing, but they are not. We will see the difference during this lecture. And then there is address, which tells you where the variable is stored in your memory and how it can be accessed. Now that we are talking about how it can be accessed, we need to talk about access rights, which essentially tell the program who can access this variable, and once they've accessed it, what they can do with it. Can they read it? Can they write into it? Or things like this, right? So before we look at variables, let's look at what binding time means, right? On a high level, meanings to variables can be bound at different points during your program execution or compilation, or even sometimes, as the name indicates, language time, in the sense when your language is defined. For example, meanings of operators in languages that don't allow operator overloading, which redefines the meaning. In some languages, operators meaning is defined when your language is defined, a language is designed and implemented, right? For example, plus means arithmetic plus when the language is defined. The more interesting bindings are static binding and dynamic binding. Static binding essentially binds a meaning to a variable during compile time. For example, this code snippet double deval in Java. The type double is bound to deval when Java is trying to compile your program. The other form of binding is dynamic binding, where an attribute is bound to a variable only when the program is being executed. For example, consider the value of deval in this small code snippet from C. Deval equal to 2. If a particular condition is met, then deval equal to 4. Here, the value of deval can be value 2 or 4, depending on the condition, can be bound to deval only during execution time. So these are the different times a particular attribute can be bound to a variable. Of course, with modern language workbenches where you create your own languages, you can have any number of bindings and any number of times the bindings happen, right? So hopefully you will explore some of them during your mini project using MPS. Okay, so let's look at the first of our bindings, aka scopes. There are 2 different kinds of scopes, static and dynamic. Let us look at static scopes first. So essentially, in static scopes, as I mentioned before, a scope tells you in what part of the program your variable is visible. In static scopes, essentially this means in what set of statements or sentences your variable is visible. What do I mean by visibility here? Within these statements that your variable is visible, it can either be referenced or assigned or modified to a different value or things like this, right? Now, there are many ways your language searches for what the scope is, but one of the common processes for searching for the scope is generally to start with where your variable is used or referenced or assigned, right? And then it branches out into larger scopes till it reaches a point where it can find the definition of the variable. Now let's look at this example where in function sub2. So this is a simple example with a function big which has two subfunctions sub1 and sub2. Both of them do something with the variable x, right? And also variable x is defined outside, right? So this is a simplified JavaScript example. Now, depending on the search process that I just described before, what would be the value of x at the point that it is referenced in sub2? It would look at the function sub2, the scope inside sub2, it's not able to find anything, any definition of x, it would branch out. And at this branching out, you should understand that sub1 scope is still not visible. The bigger scope is the function big, and then the variable's value x is, the value of x is 3, and that would be the value that is bound to this variable at this particular time. So the scope involves the scope var x equal to 3 inside the function big, and then the scope of sub2 itself at this point. Now, as I mentioned before, scoping rules can vary per language. In order to drive this point home, let's look at a code example that can be valid, not valid, that let's assume that we have versions of this code snippet in C, Java, and JavaScript. Of course, in JavaScript, you will have to replace int with var. So when we look at the C variant, let's consider the int version. So the program would be int x equal to 1, if true, int x equal to 2, and then print x. Now here, the value of x during the point it is printed would be 1 because C just assumes the scope of this variable or scope of this variable at the point of print x to be the bigger scope, this bigger block. At that point, the value of x is 1, so even though inside the block the variable is redefined as 2, it would not be counted. But in languages like JavaScript, where you have the var version, it is, if the condition is true, the variable, the value of the variable x is redefined at this point, so when you're printing, it would actually print 2. Languages like Java take a rather safe approach. If you redefine a variable inside a subscope, it's essentially going to throw an error saying, hey, you have redefined the variable again, and multiple definitions of the variable, declarations of the variable x are not allowed. So this is to drive home the idea of what the different possibilities are for on how languages define static scopes. Now, another important thing to note is that before we were talking about declarations, different languages have different ordering of declarations that is allowed. For example, in the C89 family of languages, all declarations of variables inside a function should happen at the top. This kind of improves readability and organization, but is probably not that helpful. Maybe it doesn't even improve readability depending on who you talk to. So this is one design choice that C89 has taken. In C99, Java, and C++, and the modern variants of C-like languages, declarations can be placed anywhere a statement can exist, right? And also modern languages like C++, Java, and C# allow you to declare variables inside loops or inside loops. For example, you can, in this small function, it has a for loop. We'll look at, again, loops later in the talk. But in general, loops allow you to iterate over a particular set of statements again and again and again. So here in this for loop, I want to use a variable count which should exist only inside the scope, so I define it there once, right? And then I do some things like this. So this is to provide you more convenience for declaring variables for different programming constructs. There are special kind of static variables called global variables, which have what is called a global scope. And as the name indicates, global scopes are variables that are visible outside all blocks, meaning all functions, depending on your language, which is the broader scope, be it a class or a function. Global variables exist outside, and they are visible outside all of these blocks. Now, they are allowed in some languages like C, C++, and Python, and JavaScript. And handling of these global variables are different across different languages. Because this is a rather non-trivial concept, we'll see a couple of more examples in a couple of more languages, but most popularly in C, if you have defined a global variable that exists outside a function but that's not defined on the top, you would have to use the word extern to say that, hey, this particular variable is going to be used throughout my program or even outside. All right. So to show how global scopes are handled with other languages, let's look at, for example, PHP. This is a program where globally 2 variables are defined, day and month, set to Monday and January. Then there is a function calendar, which reassigns the value of day to Tuesday. And then you use the keyword global to say that from this point on, the variable month inside this function calendar is going to refer to the global variable month. And then you have a couple of print statements. And if you notice, one interesting thing here is the globals array. Essentially, this means that if a local and a global variable share the same name as here, which is the day, the globals array can be used to access the global version, right? So, and you have a couple of print statements. So how this would execute is that the first print would say that the local day is Tuesday, referring to the local day variable, and then you have assigned gday to point to the day from the global version. So the global day would be Monday, which is coming from the global variable, and then of course the global month will be month, because you've said I'm going to be accessing the month inside my function is going to refer to the global month. So another example of how global variables are handled with Python. Let's incrementally make the program more and more complicated. Right? So first we start with a simple program where there is a global variable called day, which is set to Monday, and there is a tester function which says that print blah 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 global day is day, and then you call tester. Now it would just obviously do what it has to do, which is print global day is Monday. Now let's enhance the program a little bit. We say that the day, after our first print, we reassign the value of day to Tuesday, then we print the new value. Now this is going to throw an error because the first print global day equal is day, first searches if there is a variable available inside my scope, which would lead to the definition of day equal to Tuesday in the second line of the function tester. And this would cause an error in Python because forward referencing is illegal in Python. So in order to make such assignments possible, you can declare the variable as global at the top of the function. You can, so how you do that is you would say, you would define tester, you would say that this global day is referring to the global variable, then you would say the global day is whatever, and then you can now redefine the variable, because the first print statement is actually searching for the definition of day, but it's already coming at the top saying, hey, just look at it from the global variable. And then you're reassigning it, and then the next print statement would essentially look at the local definition of A, which is Tuesday. Now that we have seen static scopes, let's look at some advantages and disadvantages. One is because of the flexibility that static scopes provide, they kind of work well in many situations, but you can also provide too much access to variables and play around with the static scopes a lot. And the more important disadvantage is that if your software evolves, meaning your programs reassign or use variables at different points of programs, the scope keeps changing depending on where you throw and where you remodify this variable. Newer languages use the concept of encapsulation to control access to variables to mitigate the disadvantages that static scopes provide. Now let's look at what a referencing environment is, which enables scoping to be possible, right? So a referencing environment, so this is useful for both static and dynamic scopes. So a referencing environment is essentially a map of visible names, right? Depending on whether it's static or dynamic, the word visible changes to active, which we'll see when we go into dynamic scoping. It's just a map of names to the bindings at that particular point. So a referencing point is constantly updated along with backups in more complicated languages to say, okay, this is the meanings that can be associated to this particular variable at this particular point. Now, looking at the simple example, there are a couple of variables, x, y, which are defined to be 20 and 10. Then there is the variable z, which we can assume is defined elsewhere to be an integer, and then it's used in the conditional, and then string x equal to something, and so on and so forth. So the referencing environment at the point after string x, after the statement string x equal to something is done, would look something like this. So x would have a couple of meanings. One is the type, which is string. The other is the value, which is something. Y and z would have the same meaning, type, which is int, and then the value of y would be 20. Sorry about the typo in the slides. All right. Now, as you can see, the important thing is the value of x was 10 before, but if your programming language allows you to completely redefine variables at a later point, it would be reassigned to string. So that's why at this point in the referencing environment, you don't see the value 10 or the type int for x at this point inside your conditional. Now let's look at how referencing environments are updated as and when your program executes. Now let's look at how static scopes influence the referencing environment. Let's consider a simple program and assume that x is initialized as an int somewhere before in this program snippet, and in this particular block, x is assigned the value 1. If true, then x is assigned the value 2, and then x is printed. So when we get to this code snippet, the referencing environment would rather look very simple. You have an x, it's bound with the meaning int and nothing else. After the point of the first line, the referencing environment will also be updated to reflect that x is now assigned with the value 1. And now we are going into a nested scope. So in this conditional, the value of x is 2. And as mentioned before, in languages that have static scoping where it searches for the scope outside, at this point, the value of x will be reinitialized to 1 because we have branched out of the nested scope, and the referencing environment will have a backup of the value 1. It will be assigned to 1 at this point, and then which is what will be printed. Now, this is how referencing environments are impacted by static scoping. Now we come to the end of our discussion on static scopes. Now let's look at another scoping mechanism called dynamic scopes. Static scopes are defined based on how your instructions are structured, but dynamic scopes also have the concept of visibility of what variables mean at different points of your program and what is visible, who can modify them, but this is influenced by the calling sequence of these functions. Let's look at a code snippet from a language that uses dynamic scoping, the Born Again shell language, which is a scripting language for the Linux operating system. The example is similar to the examples that we saw. There is a variable x which is assigned to 1, which is global. There's a couple of functions. One of them prints the value of x. The other function g, which creates a local instance of the variable, assigns it to 2, calls f, and then finally in the main program you have a call to function g. Now, as I mentioned before, dynamic scopes languages that use dynamic scopes determine the visibility based on call sequence, which means you need to have another thing on top of your referencing environment called the call stack, which essentially shows you what is the last function that was called. At the start, we just only the main function is called, and the referencing environment has x with nothing bound to it. Now, at this point, still nothing is bound to it, and then we are looking at 2 particular definitions, so nothing is done, right? And of course, the value is assigned to 1 because on the top of the call, the value is assigned to 1 in this main call, in the call stack where only main is called. Then there is a call to g. At this point, g is added to the call stack, and then we parse through the individual instructions inside g. So we have assigned a local variable x, which still refers to the same variable x. Its value is reassigned to be 2. And then there is a call to function f, and f is added to the call stack, and then x is executed, At this point, the value of x is 2 because we use dynamic scoping. If we had used static scoping, the search process would have been that at the point when you're typing echo x, it would branch out to the main function and the value of x would have been 1, and then that would have been printed. But because the call sequence determines what the value of x is at this point, because g is the one that called x at this point, the value of x would be 2. And then once we are done with x, f is pushed out of the call stack, value of x is still 2, and then g is pushed out of the stack once, or popped out of the stack once g is done executing. But at this point, the value of the variable is 1 because in the call stack where main is the only thing that is available, the value of x is equal to 1. So, of course, one bizarre thing to note here is that actually bash uses the mechanism of calling functions without parameters with just the name, nothing else, which seems to work out for people who write scripts. So now we have seen static scopes and dynamic scopes and how referencing environments are impacted by both of these. Now that we are done with scopes, let's look at 2 more bindings that can be associated to variables. We'll discuss storage and lifetime together because they go hand in hand. So, lifetimes. To understand lifetimes, we need to understand that variables don't exist all the time in memory. They have what is called a lifetime, right? The lifetime of a variable is when lifetime of a variable begins when it's allocated and completes when it's deallocated. Between this time, the variable kind of exists in the universe of the program, right? And this allocation and deallocation methodology changes according to language. Some languages prefer to do at least one of these automatically, sometimes both of them, and some prefer to provide the programmer with complete control when and how he does this allocation and deallocation. There are advantages, disadvantages to both. Now, as I mentioned, allocation, deallocation depend on the language, but they also depend on what kind of variables are being used and the memory location in which they are stored. Memory locations available are multiple things, but 2 most important things are the stack and the heap. Stack is where things are stored on top of each other, with the top one being popped out or retrieved first. Heaps are hierarchical data structures that is allocated randomly and implemented using arrays or trees. Discussing beyond that for stack and heap is kind of not in the scope of this lecture, but hopefully the different allocation and deallocation strategies that we will discuss will shed some light into these. So the first kind of allocation strategy for variables are for this kind of variables called static variables. Static variables, as the name suggests, are stored in static memories. Static memories are locations which have a predefined size and kind of exist throughout the program. There is no explicit allocation or deallocation because the variable exists also throughout the program. Global pointers also point to static memories, which is how you access these static variables, right? So essentially how you find out where your variable is in the static memory depends on what the global pointer is, right? So that's how you access the variables. Here's a small example from the C family of languages. It's a function, static int c equal to 0, and you do some increment with this variable c. Now, because you've said it's static, it actually, even though it occurs within the scope of a program, the variable c is assigned a location in the static memory. Now, the next kind of variables are called stack dynamic variables. So, as the name suggests, they are stored in the stack. They're perhaps the most common kind of variables, and generally the allocation begins when you enter the scope of the function or the block, and then it is deallocated when you leave the scope. And we have discussed enough about how you determine the scope of a particular variable. So, and programming languages are generally intelligent or clever enough to know when the scope starts and ends, right? And we also discussed how it varies per scope varies per programming language. Now, stack variables are very attractive because their lifetime corresponds to the blocks or the particular scope you define them, which means there is a strong connection between the code structure and to this particular kind of stack memory. And for referring to these variables, we use what is called the frame pointer, or in some cases the stack pointer. So essentially, frame pointers are used by high-level language compilers to track what's happening, what's the current variable in the stack frame. Some examples of them are local variables and parameters, as I mentioned before. And then the next kind of variables are heap dynamic variables. These are a little bit more flexible to use than stack variables, but also they also pose more difficulties because in many languages you have to explicitly allocate and deallocate them. There's also other challenges with the access itself. Modern languages kind of implicitly allocate based on syntax, and some of them also deallocate based on automatic memory management techniques, and which essentially garbage collectors like the ones used by Java allow you to allow the system to do, so you don't have to explicitly deallocate. As I mentioned before, these are a little bit more flexible, which means the lifetime is also rather flexible. It's not bound to the stack or it's not bound to the scope of your code structure in which the variable occurs, or it's not bound to the whole program itself, like the static variables. The address can be anywhere on the heap, so finding stuff on the heap can be tricky. You can use pointers and carry these pointers around, like this example shows, where you have a string. Essentially, the star says that the C is a pointer to a variable whose type is string, right? And in C++, you also at the end say, you delete this particular variable C. Now, we'll see the difference between pointers and references later in the slide, but essentially you can use these pointers and carry them around. This is dangerous because pointers can be modified at a later location, continue to be modified, and then it can happen that you modified your pointer so much that you can't even find the variable anymore. So that's why you will always hear the phrase pointers are a dangerous thing. So be careful with them. Now, since the concept of heap dynamic variables is a little bit more non-trivial, let's spend a little bit more time on this. Right, here is a simple example of code in Java where we don't use pointers, but we use references. And as mentioned before, references and pointers are different. But for now, let's just look at them similarly. I'll show you a glimpse of the difference in the upcoming slide. But so references here, S points to a variable of type string with the value foo. That's what the string s equal to neo string foo does. But essentially, the place in the heap where foo is stored doesn't have any name. It's just another variable called s, which is pointing to the memory location that contains foo, and then string s2 equal to s essentially says that I'm going to create another variable, so a third variable here, which would point to the same location that s was pointing to. So it would essentially have a copy of the reference that s has. These are some examples of how heap variables are assigned and allocated and deallocated based on different languages. In C, you would use malloc to allocate, free to deallocate. In C++, you would use new to allocate and delete to deallocate. In Java, again, you would use new to allocate as the example shows, but the deallocation is implicit because Java has a garbage collector which takes care of everything. Now, heap variables can also be implicitly allocated, in the sense you don't explicitly create any variable that references or points to a heap variable. Here's an example in Python where you're defining a function and it just returns a list that contains one of the parameters of the function, in this case x. Now, the program is rather simple, but for the function to function, right? The value 1, x, 2, which is a list, and it needs a memory location to exist. So in your heap, an implicit heap variable is allocated, and of course deallocated implicitly too, in the case of Python. So I mentioned before that there are two different ways you can handle heap variables, references, and pointers. Although they appear to be the same, they are actually very different, right? References are used by languages like Java, where a variable can point, essentially a reference is a variable that points to some other variable or nothing, right? It just refers to it. So there are memory locations without any name, and then you give a name to kind of refer to it. That would be references. So of course, references can also be to nothing. Depending on languages, the nothing is defined by different words: null, nil, none, whatever. Right? Pointers are a little bit more flexible than references, in the sense pointers can contain any arbitrary memory location. It can contain a memory location in the middle of a string. It can contain a memory location that points to a middle of an assembly instruction, right? You can imagine that this can open up all kinds of security holes. An attacker can simply manipulate your pointer to point to an instruction that just deletes all the files in your system. So of course, that means that pointers can be very dangerous. But also there are some kind of systems programming that cannot be accomplished easily without having access to memory locations. So they are also vital to many kinds of systems programming, which is why C and C++ and pointers are still very popular. So here's a summary. Here's an example which summarizes a different kind of lifetime for different kinds of variables that we saw. Here's a simple C program. It has a function f, which takes in a parameter x. Inside it locally defines one variable integer called y, and another variable called a, which is a pointer that points to a memory location which can hold, which allocates memory enough to store one integer. Then you're defining one more static in C, and then finally there's a global int x. Now the memory locations of the first parameter x will be in the stack. Int y, which is a local variable, which will also be in the stack. Now in star a, the pointer which has the address to another location will be stored in the stack, but what a holds, right? The memory location will point to a memory in the heap where the value of a value that is pointed to by the memory location stored in a will be there, right? And of course, static in C, even though it's happening inside a function because because we have marked it as static, would go in the static memory, and then int x, because it's global, which exists outside all functions, would go inside the static memory too. So this is a summary of different lifetimes based on different kinds of variables and where they are stored in the memory location. So the final binding that we will see today is access rights. Although access rights sound like visibility, they are quite different, right? So visibility visibility is used by programming languages to say, hey, I don't even know what you mean by x, right? So in the right-hand side, there's a function f, and there's a condition const equal to x, and then outside the scope you say x equal to 2. Well, the programming language would throw an error saying, I don't know what you mean by x, right? But with access rights, your programming language very well knows what you mean by the variable. It's just not going to allow you to do it. So here you've defined a variable int x and assigned it to the value 1, and you've said it's const, meaning you can no longer write into it, you can only read from it. Which means when you say x equal to 2, you're trying to write into the variable. The language knows what x means, but it's simply not going to allow you to do whatever it is that you plan to do with it. Right? So that's the difference between access rights and visibility. So with this, we have come to the end of today's session. I thank you very much. In summary, we have discussed a very important abstraction that programming languages provide, aka variables. We saw what are all the properties or attributes that can be bound to variables to provide meaning to these variables. We saw around 7 of them, and then we discussed all of them except types in pretty exhaustive detail. And we will look at, of course, types much later. So thank you very much.